Welcome to Chemistry 111. Hopefully you had a good Valentine's Day. I'm rocking my Valentine's Day Rastafarian hoodie. But in the snow day, as we're doing it online, we'll deal with this. Can't go over last test crib yet. All of the tests I haven't are graded. I'll maybe load up the grades online with some sort of curve. I have written next test, so that's all ready. I just gotta check a few things. I may not give that out till Wednesday or so, Wednesday or Friday, I don't know. But today we will go ahead and go through last year's test so you can see what type of questions I asked. It's not going to be too dissimilar from the take-home test. The only difference being that a lot less multiple choice. Well, no multiple choice at all. But this take-home test will probably not be too difficult, all things considered. I didn't throw too many crazy hard problems on there, not like some of the ones. Well, I don't think this one test was that hard per se, not like Chemistry 112 hard. But so we're going to start looking at the last test in just a second. There we go. Okay, so with that in mind, let's go to last year's test, opening from Microsoft Word. So as you see, well, some of these problems are not too dissimilar from what you're going to have. Let's read through the entire test real quick, just so the first two questions have to do with the wavelengths of light and turning frequency and wavelengths into energy, and frequency into wavelength and energy. We have electron configuration problem. We have an isoelectronic problem. We have a trend problem. We have a condensed electron configuration problem. We have electron diagram and pairing electron problem. We have a electron configuration of an ion problem. We have a condensed electron configuration problem for number 10. Number 11, we will not see at all because we have not done that in lab. But that was a lab-based problem of Beer's law that absorbance equals 1 times, essentially, molar absorptivity times path length, which is always 1 times concentration. We're not there, so we're not going to worry about anything like that. Electron configuration, ionization energy, wavelength energy problem, quantum question about p orbitals, unpaired electron problem, electron configuration problem, lattice energy, another lab-based problem we're not going to do, atomic radii, let's see, electron configuration of ion, radius with isoelectronic. Let's see, we had 25 problems. 8 valence electrons. Say, the quantum problem, and then one more electron configuration problem. So we had 25 problems, 2 of which are lab, the majority of which are very similar to what we will have on the test. So let's start with looking at this one. A standard microwave oven produces 2.45 gigahertz. 45 gigahertz frequency. Please note, 1 hertz is equal to 1 inverse second. The first question asked is, what is the wavelength in millimeters? And then what is the energy in joules? So to do that, we're going to go to the dot cam. The order is from the hertz. Hertz is smaller than kilohertz, which is smaller than megahertz, which is smaller than gigahertz. 10 to the third, 10 to the sixth, 10 to the ninth. Kilo, mega, giga. So this is the same as 2.45 times 10 to the ninth hertz, which is equal to 2.45 times 10 to the ninth inverse seconds. Because 1 hertz is equal to 1 inverse second. Now, the first question is, what is the wavelength? So the equation for wavelength is C equals lambda nu. So wavelength is our lambda, frequency is nu, C is our speed of light. So in order to do this, I'm going to take C divided by our frequency to get our wavelength. So C is 2.998 times 10 to the 8th meters over seconds. And by dividing by our frequency, 2.45 times 10 to the 9th inverse seconds means that's going to be 1 over seconds. Seconds cancel out. This math will leave us with, conveniently, units of, units of meters. 2.998, let's see, times 10 root 8 divided by, let's put this in parentheses, 2.45 times 10 root 9. That puts this, how many meters? 0.122 meters. However, in this question, I ask you for the answer in millimeters. So to go from meters to millimeters, we multiply by 1,000. So the correct answer should be something like 122 millimeters. Okay. Second part of this question, what is the energy? Well, energy is equal to H nu. H is a constant, 6.626 times 10 to the negative 34th joule seconds. So if you multiply this by our frequency, which remember was 2.45 times 10 to the 9th inverse seconds, seconds and seconds cancel out, we're left with answer of joules. So plug that in, 6.626 times 10 root negative 34 times 2.45, 10 root 9. I got a really small number, 1.62. If I'm doing correct sig figs, this has 1, 2, 3, 4 sig figs. This has 1, 2, 3 sig figs. So that had 3 sig figs. So 1.62 times 10 to the negative 24th joules. So that is how you would do these. So don't trip up. You might have to go from wavelength to frequency and frequency to energy, but that's just a two-step problem. The hardest part here is making sure you're in the right unit. Make sure if you have nanometers, you have to convert to meters. If you have megahertz or kilohertz, you convert it to hertz, which is an inverse second. If you do that, this part should not be hard, but this is dimensional analysis at its easiest. You just have to make sure you convert to meters or from meters to something else. And that's just two equations. Okay, so that puts us there. Okay, the next one. What is the full electron configuration of gallium? Full electron configuration of gallium. So we need gallium. Here's where we need to pull up a periodic table. Now, I may not have a periodic table on the test, but do know you have the internet. There's no good excuse for why you shouldn't be able to look this up. So gallium for me is right there. So working my way across the table. Starting with helium and hydrogen. You're going to say 1s2, end of the row. Then I go lithium, beryllium, 2s2, 2p from boron to neon, 6. Sorry, I go back to the doc chem. Gallium is right here. Right there, right below aluminum, 2p6. So I went 2s2, lithium, beryllium, boron to neon, 2p6. Next row, 3s2, 3p6 gets me to argon. Then 4s2. Here's the tricky part. We've hit the D's. D is always row -1. So since it's row 4, it's 3d10. And then gallium would be then 4p1. So the full electron configuration there is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p1. Now, there is some sort of Christmas tree method to help you remember what order they go in. I don't hold much truck with that because I've seen someone draw the Christmas tree wrong and then they get this totally backwards and they don't even have the slightest clue why they did it wrong. I would rather have a periodic table and label all these rows. These are the S. These are the P's. These are the D's. These are the F's. And then I'd put above the D, row -1. Above the F, row -2. And you just work your way across. You just work it one element at a time, one row at a time, one group at a time. And it's really not that hard. But remember, full electron configuration means everything. Condensed means we shorten it, as we'll see. Which of these ions would be isoelectronic with calcium? So calcium, it means isoelectronic means same number of electrons. Which of these guys would be isoelectronic? So let's look at the periodic table again. Calcium. Calcium is right here. So 2 plus means it's going to have the electron configuration of argon. So we got to figure out what thing would also have the electron configuration of argon. Chlorine 1- would have argon. Sulfur 2- would have argon. Potassium 1+ would have argon. Titanium 4+ would have argon, but let's look what options we have. Titanium 2+ would not be there. It would be moving 2 elements to the left, not quite. Strontium 2+ would be like a noble gas. Bromine 1- would be like a noble gas, but it would be the wrong noble gas. Only chlorine 1- would have argon. Chlorine 1-. Only chlorine 1- would be moved over to argon. So the correct answer is chlorine 1-. Now, we need to describe in our own words the ionization energy trend both through the group and down a period. Ionization energy is the energy it takes to remove an electron from the remove the electron from the highest energy orbital in when the element is in the gas phase. The trend follows that. As we go across the table, the ionization energy increases because of the increasing Z effective and the decreasing size. As we go down the table, ionization energy decreases because the size greatly increases, making it easier to remove the electrons. But describe in your own words. So that means if you choose to work with someone, if you're working with someone, please don't just directly copy their words for word. Reword it. It's okay if you both have the same idea. Reword it slightly. Just make sure it still essentially says the same thing. Don't accidentally reword it in a way that suddenly you're saying something that's no longer true. Okay. But I had some people in my 112 who directly copied word for word on word problems like that. And I had to penalize them because it's use your own words, people. Don't plagiarize. And I can't tell who's the one who wrote it first, so you both lose points. So don't do that. So which of the following is the correct condensed electron configuration for Tallium? Remember, Tallium, well, condensed means you start with a noble gas, and then we work our way from there. Tallium is what? Oh, tantalum. Sorry, tantalum is in the D block, and this is a hard one. This is a weird one. Tantalum is right there. So starting from xenon would be 6s2. And then it's weird because it jumps directly into the FL orbitals. 4f14, and then it goes 5d 1, 2, 3. So you should have 6s2, 4f14, 5d3. So correct answer is D. B completely leaves out your f orbitals. A is essentially right, but it's the wrong row. And B is essentially right, but the wrong number of d electrons, and also left off the xenon. So the correct answer is D. Now, which of the following energy diagrams use it as the following question? So sulfur. So put electrons in for sulfur. Sulfur is element, God, it was 16. So you're putting in 16 electrons. How do you answer this one right? How do you answer this one right? You have to put in electrons up the orbitals, and you have to make sure you do it right. But it's really hard to do it wrong. There's really only one way to do this wrong. Well, there might be two. 2, 3, let's see, 4. Yeah, this should be more than enough to do 16. So look at this. And then how many valence electrons are unpaired? So we have to do 16. So we start from the bottom and fill it up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There's 16 electrons. That's where we stop. The big thing here is not whether they're up or down. It's whether all of them are up or all of them are down before you start flipping it. I could have done this. I could have done this. Down, 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 up. But you start with all of them in one direction before you pair. But that's fine. Doesn't matter how you pair them. Doesn't matter. I could technically put all here and then pair this guy. They're all the same energy levels. It's not standard, but you could do that. That's a valid thing. The important thing is when you pair them, they're flipped. They're spin flipped. One's up, one's down. That's the only way you can really screw this up. That's the main way to screw this up. You could have done this. This has also been wrong. That would have also been wrong. But so, okay, so drawing the electron configuration, that's that. How many of these guys are unpaired in the valence? 1, 2. 2 unpaired valence electrons. So we've essentially answered the second part of that question by correctly doing the orbitals. No, making reasonable time. Okay. What two ions would have the same electron configuration of 1s2, 2s2, 2p6? So here's one that really takes you to think. 1s2, 2s2, 2p6. I want ions, not neutral, ions. So go into our periodic table again. 1s2, 2s2, 2p6 is neon. So what ions would have electron configuration of neon? You could have said F1 minus, O2 minus, N3 minus, carbon 4 minus, or sodium +1, magnesium +2, aluminum 3+, silicon 4+. Any of these are possibilities. All of these would have be isoelectronic with neon. All of these guys would have the same number of electrons as neon. So you had to think which one of these had that correct electron configuration. Now, condensed electron configuration of titanium 2+. This one is a tricky one. It's 2 parts. Titanium 2+ is down here. Let's just do titanium neutral. When people screw this up, typically they do titanium neutral. But titanium neutral would be argon, then 4s2, 3d2. That's titanium. Now, titanium 2+, you remove 2 electrons. So you start, the rule for removing electrons is P, then S, then D, then F. So with that in mind, we don't have any P's, so we move on to the next one. We move from the S first. So 2 electrons means we go check, check. So the correct answer would have been argon 3d0. Had you given me titanium neutral, you probably would get half credit. Had you done the full condensed, full electron configuration, but titanium 2+, you would have gotten maybe half credit. But so that's that. Remember, we remove S, we remove P, then S, then D. So that had I said 4+, I would have then removed the 3 Ds, and I would have been just down to argon and just argon. Okay. Skipping that one. Condensed electron configuration of phosphorus. condensed electron configuration of phosphorus. So we go into there. Phosphorus. A lot of this test can be done directly from the periodic table. So phosphorus, right there. So we start from neon, which is row 2. So we'd go 3s2, 3p, 1, 2, 3. That's all it is. Not a hard one, just one where we ask you to think about it for a second. Which of the following elements is likely to have the following ionization energies? So this one you look for where is the humongous jump. So 7, 8, which one of these jumps is so much bigger than the others? 787, 1577, with 3,231. Either of these jumps could be the big jump. Maybe 4,000. Okay. Then 16,000. Then it's like, oh, no, there's the obvious jump right there. This is a jump of about 1,000, about a jump of about maybe 1,000, almost 2,000, jump of maybe another 1,000. Jump from, instead of like 1,000 or 2,000, it jumps by 12,000. Then from there, it's another 3,000 or so. Then another 3 or 4,000. But 12,000 is the big jump. So we lost 1 electron, 2 electrons, 3 electrons, 4 electrons. 5 electrons are no dice. No dice on losing 5 electrons. So what element can lose 4 electrons? An element in group 4A. Aluminum is in group 3A. Silicon is in group 4A. Phosphorus is in group 5A. Sulfur is in group 6A. So silicon is the correct answer. Next question. What is the energy of average? What if the energy of an average medical X-ray is 1.60217 times 10 to the negative? I'd like to say 15th. I'm going to pull that up. Negative, I think that's 15th. What would be the wavelength of X-ray? I'm going to quickly... Yeah, that's 15. So what would be the wavelength of that X-ray? So this one, we're asked to go backwards a bit. Go backwards a bit. So we're going from energy to frequency, frequency to wavelength. And then we're going to, so C over lambda, frequency. So we'll start with 1.60217 times 10 root negative 15 divided by RH, which is 6.626 times 10 root negative 34. Please note, I'm putting these in parentheses so I don't screw this up. I get the first thing, I get the frequency. I'm writing that down, 2.418 times 10 to the 18th. Next up, 2.998 times 10 root 8 divided by my frequency, 2.418 times 10 root 18. Gives me a really small number. We do that, we get the lambda is equal to 1.23, we'll say, 24 times 10 to the negative 10th. I'm just rounding unnecessarily, but okay. Now, looking back, the options. We want these in the correct units. So This one, in order to make it harder, I made a bunch of different answers, some of which in the right unit, some of the wrong units. They're all pretty similar. A, C, and D are all pretty darn similar, but one is 10 to the positive ninth meters, which is wrong. It should be negative ninth or negative 10th. If I multiply this by 1,000 to get this into millimeters, not quite there. If I multiply 1,000 again to get it micrometers, still not quite there. Multiply it by a third set of 1,000 to get in nanometers. We say the answer is A. Well, you won't have this issue because it is not a multiple choice test. B is technically right if I'm asking for frequency. And I would often do this where I'd give you, hey, it's a frequency. It's a correct number. If you got that and you saw that, oh, hey, I got the number, you didn't answer the question. So B is technically right in the standpoint you're doing it right, but you're not answering the question, which is wavelength. You're giving me a frequency number. So A is the correct answer. The next one, in your own words, describe the shape of p orbital. So, well, I'm not going to necessarily ask you this, but it's a dumbbell or a figure eight or infinity sign, or it's asking you to think about what S is just a sphere, P is the figure eight, the D is like the clover leaf. This one, using the electron diagram from above, how many electrons would be unpaired in the element iron? So, using it from up here, back up to here, iron is the, sixth element into the d orbitals? Sixth element, so you would have filled this all the way in, and you put 6 in. 1, 2, 3, 4, 5, 6. So that means 1, 2, 3, 4 are unpaired. But full electron configuration of lead. Oh, that's a brutal one. That is the first one that's going to be actually hard kind of thing. Just because it takes such a dang long time. Full electron configuration. Lead is right over here. And it's just working our way across. All the way, we have to get to row 6. So 1s2. 2s2, 2p6. Then 3s2, 3p6. That's row 3. 4s2, 3d10, 4p6. That's row 4. Almost there. 5s2, 4d10, 5p6. That's row 5. Last row. 6s2. Now here's the hard part. It jumps down to the lanthanides and actinides. So 4f14, 5d10, because we got to do all the way to mercury. And then lead is 6p2. That's a brutal long one. I had a lot of people when they took this test confuse condensed electron configurations with full electron configurations. Please don't do that. Full means the complete thing. Condensed means the shortened one. Lattice energy problem. This one's actually, if you understand the concept, it's not hard. Let's write these guys down. Step 1 is looking at the charge of the cation and the charge of the anion. Step 2 is then comparing the size of the two. So charge comes first, then comes size. Beryllium is 2+. Oxygen is 2-. Sodium is +1. Fluorine is -1. Sodium is +1. Oxygen is 2-. Magnesium is 2+. Oxygen is 2 minus. How did I do that? Periodic table. Boron. Oh, sorry. Move this up here so we can see it. Beryllium is right here. Oh, for God's sake. Beryllium is up there. Magnesium is right below it. Oxygen is right there. It moves 2 elements to the right. Fluorine is right there. Moves 1 element to the right. Sodium is right there. It can move 1 element to the left. So, with that in mind, which one of these are the most highly charged? 2 plus and 2 minus, 2 plus and 2 minus are going to be, these guys are based on charge, I would say 1 and 1 prime. These guys are going to be the biggest lattice energy, followed by 1 plus and 2 minus. That's going to be 2. And 1 and 1, that's going to be 3. That's going to be the lowest lattice energy. So the next thing is size. The smaller the size, the higher the lattice energy. So the question becomes, which one's bigger? Beryllium or magnesium? They're both have oxygen, but beryllium is here, magnesium is there. So as we go down a table, size increases. So this one is actually the number 1. This guy is actually 2. This guy is 3. This guy is 4. So put in the correct order, you would have this guy lowest, second lowest, second highest, highest. And that's what you do for the lattice energy. Skipping number 19, since we don't have to do that one. Place the following atoms in order of decreasing atomic radii. So the smallest ones on the right, biggest ones on the left. So in fashion, let's look at where these are on the table. We have lithium, fluorine, calcium, gallium. So lithium is row 2, 2 on the left. Go to the .chem. 2 on the left because lithium right all the way over there. All the way over there. Fluorine, 2 on the right. Row 2 on the right. Calcium is 4 on the left. Gallium is row 4 on the right. Not quite all the way on the right, but on the right. Typically speaking, if I would say comparing rows, you're going to have the right is smaller than the left. As we move across the table, size decreases. As we move down the table, size increases. So let's say the biggest one would probably be calcium, followed by probably gallium, followed by lithium, followed by fluorine. However, I'd have to look on here. Let's see. I might actually have a size chart. Maybe, maybe not. No, I did not. Okay. Sometimes I actually included the size chart, which made it a lot easier. But that's how I would justify that. Write the condensed electron configuration of ion and the iodine and the condensed electron configuration of tin 2. So iodine and tin 2. Iodine right over there. So iodine, start from krypton. Start from krypton, which is row 4. So we start 5s2, 4d10, 5p5. Now, tin neutral. Tin neutral is also row 5. So that would be krypton 5s2 4d10 5p2. So to make it tin 2 plus, we would cancel out that, and that becomes 5s2 4d10. So we remove the p and then the s. So since we only had 2 electrons to remove, we had 2 electrons in the p, we only removed the p. Place the following in order of increasing size. These are going to be hopefully isoelectronic, which will make this easier. Okay, isoelectronic system. Isoelectronic. So we have Br minus, rubidium plus, selenium 2 minus, strontium 2 plus. If these are indeed isoelectronic, the rule of it is the larger the negative, the bigger the size. Larger the negative, the bigger the size. So let's look. Bromine 1 minus is going to be like krypton. Rubidium plus 1 is going to be like krypton. Strontium 2 plus 1 2 going to be like krypton. Selenium 2 minus is going to be like krypton. So these are indeed isoelectronic, meaning if I need to put them in order of increasing size, I'm going to want strontium 2 plus being on the left, followed by rubidium plus 1 on the left, followed by bromine 1 minus, followed by selenium 2 minus. So most positive, least positive. All because the size increases with increasing charge. 2 questions. What group would be characterized with 8 valence electrons and its highest principal valence energy? An unwillingness to make any bonds. So what group number? Instead of the A's, I'm using the standard group number. And that is actually group 18. Though I probably should have accepted A, which is 8A, but the correct answer was going for is group 18, which is the noble gas group. And the last question, Mackenzie Police uses a radio channel of 37.4 megahertz. What is the energy generated by this wave? So 37.4 megahertz. So remember, mega means 10 to the 6th. So times 10 to the 6th hertz in a megahertz puts us at 3.74 times 10 to the 7th hertz. And I say, what is the energy? So I have to say energy equals H nu. Once again, so 6.626 times 10 root negative 34 times 3.74 10 root 7. Very low energy. 2.4, let's say 48 times 10 to the negative 26th joules. So all that stuff is fair game, a little bit more, but for the most part, the test is going to be very similar to what you see there. This is going to be very similar to what you see here. So if this test right here did not seem too hard. Hopefully you'll find the take-home test to be equally reasonable. It's basically going to be, hey, can you do this? Can you do that? Can you do the full electron configuration? Can you do the condensed? Can you make the ions? Can you answer questions about the orbitals? Can you answer questions about the trends? Can you do a lattice energy problem? All this stuff is going to be what's on the take-home test. I'll probably give that on Wednesday, maybe Friday at the latest, but it's essentially written and ready for you guys. So all I'll say is thank you for your time. Stay safe, stay warm, and I will see you guys we'll speak to you guys again on Wednesday.